Welcome to Theory of Computation. This is lecture number 25. In the last lecture, we were talking about verification algorithms. The basic idea is the following. We are given a language and we want to come up with a verification algorithm for it. So what we do is we try to find a way of proving that a string is in the language, and we want to find proofs which are easily verifiable. Such proofs are sometimes called certificates. We looked at three particular languages: composites, Hamiltonian path, clique, and then in the end we were looking at the subset sum problem. We noticed that all these problems have easy verification algorithms. What we are leading towards is an alternate characterization of NP. So when you look at the Hamiltonian path problem or the clique problem, you notice something about it which is very striking. For example, if you have a graph and you want to prove to somebody that the graph is Hamiltonian, or it has a Hamiltonian path from a given vertex S to a given vertex T, the best way to do that, or one easy way to do that, is to show them the Hamiltonian path. Once you show somebody a Hamiltonian path from the vertex S to T, what they can do is they can easily verify that that path is indeed a Hamiltonian path. So they can very easily verify that you are giving them a correct proof or a correct certificate that this graph has a Hamiltonian path from the vertex S to the vertex T. Another example we looked at was the composites, the language of composite. This language consists of all those integers written in binary which are composites. Now, if you want to prove to somebody that a given integer is composite, what you can do is you can factor the integer and give them a factorization of that particular integer. What they can do is now easily verify that the product of these two factors is composite. So composites verifying a proof given like that just takes polynomial time. Another problem we looked at was the clique problem. That problem was you're given a graph and a number k, and the question is whether the graph has a clique of size k. Well, if a graph has a clique of size k, or its clique number is greater than or equal to k, how would you convince someone that the graph does have clique number greater than or equal to k? There's a very easy way to convince them. There's a very easy certificate for such a thing. What you do is you show them the clique. You tell them the vertices, k vertices, which are all connected to each other. Thus, the clique problem also has a polynomial time verification algorithm. Lastly, we started looking at the subset sum problem. And we were going to come up with a verification algorithm, which is also going to be very easy. We'll start our lecture with that. After that, we would study an alternate characterization of the class NP. Then we would look at the P versus NP questions. We will discuss what polynomial time reducibility is, and then we will discuss the notion of NP completeness. Then we will discuss a very, very important problem in computer science called satisfiability. And lastly, we would see what the Cook-Levin theorem says. The Cook-Levin theorem is one of the most important theorems in computer science. Let us begin. We start this lecture by looking at the subset sum problem. In the subset sum problem, we're given a set S of numbers and a target value little t. And the question is, if there is a subset capital T of this set S such that the elements in this subset T sum up to little t. As an example, let's look at the set 3, 5, and 7. It has the following subsets and subset sums. The empty set sums to 0, the singleton set 3 sums to 3, the singleton set 5 sums to 5, the singleton set 7 sums to 7, the set 3, 5 sums to 8, the set 3, 7 sums to 10, the set 5, 7 sums to 12, and the whole set itself sums to 15. Thus, if the input is this set and 10, then that string will belong to the language? The answer to that question would be yes, it indeed does have a subset that sums to 10. On the other hand, if somebody asks you if there's a subset of this set which adds to 11, the answer would be no. So the subset sum problem is a very, very simple problem. You're given a set of numbers and a target value, and the question is, does there exist a subset which adds up to the target value? What we want to do is now come up with a verification algorithm for this problem. So let us start thinking about the problem. What we want to do is, somehow we have an instance of the subset sum problem, we have a set and a target value, and we know that some subset of this set adds up to the target value. And what we want to do is we want to convince somebody else or prove to somebody else that indeed this is the case. Well, what would be the easiest way of convincing somebody or proving to them that this set has a subset that adds up to the target value? Well, the easiest way would be to show them the subset. Of course, they can easily verify that the given subset indeed adds up to the target value, because it's very easy for them to add up the numbers in the set and check whether that adds up to the target value. Thus, the subset sum problem has an easy verification algorithm. Let us look at this algorithm in detail formally. So formally, the subset sum problem is the set of all encodings of s comma t, where s is a set and t is a target value, such that some subset of s sums to little t. We note that the simplest proof that s has a subset that sums to t is the subset itself. Thus, the following polynomial time verification algorithm will verify the subset sum problem. What it does is, on input s comma little t and capital T, first it checks if t is indeed a subset of s. Then it adds up all the elements of capital T and checks if that is equal to little t. If that is the case, it accepts, otherwise it rejects. So, this is an algorithm that runs in polynomial time. Furthermore, if s has a subset which adds to little t, then we can provide that as a proof. On the other hand, if s does not have any subset that adds up to t, there is no way for us to produce a wrong proof and convince the verifier that this set s has a subset that adds up to t. So subset sum is another problem that has a polynomial time verification algorithm. Notice that what we are seeing is that these proofs that we are coming up with, these certificates that we are coming up with, are easy to verify. We are not saying anything about how long will it take us to find such a proof or a certificate. In the last lecture, for example, I showed you a number, and then I told you that the number was a product of these two numbers, and therefore the number was not a prime and a composite number. It may have taken me a long time to find those two numbers or factor the number. However, once I had factored the number, it was very easy to verify that my proof of compositeness of that number was correct. For that, you had to do a simple procedure of multiplication. Similarly, it may take somebody a very long time to find a subset capital T that adds up to the target value. However, once they've found it, it is very easy for them to convince somebody else, or it is very easy to verify that that subset capital T adds up to the target value. Now what we will show is the following theorem, which gives us an alternate characterization of the class NP. We will show that a language A is an NP if and only if there exists a polynomial time verification algorithm for A. Thus, we will get an alternate characterization of NP, and NP is now defined to be the class of easily verifiable problems. The advantage of getting another characterization of NP is that we can view NP from another angle. Remember that we defined NP to be the non-deterministic analog of P. So P was the set of all problems that we could solve by deterministic polynomial time algorithms. NP was the set of all problems that were languages that were recognized by non-deterministic Turing machines in non-deterministic polynomial time. Now we have another characterization, and this characterization does not appeal to the notion of non-determinism. It only talks about verification. What we are saying is NP is the set of all languages for which there are polynomial time verification algorithms. This alternate characterization helps us understand the class NP from another viewpoint. Let's start proving this theorem. What we first want to show is that if a language has a polynomial time verification algorithm, then it must be in NP. So let's begin by taking a problem A which has a polynomial time verification algorithm V. What we want to do is we want to show that this language A is in the class NP. So our task is to somehow come up with a non-deterministic Turing machine which accepts the language A and runs in non-deterministic polynomial time. Let's recall that non-determinism was like having the power of guessing. So one way to think about non-determinism is to say that our algorithm or our Turing machine has the power of guessing. Now, how will we use the verification algorithm to come up with a non-deterministic algorithm? Well, the basic idea is, since we have the power of guessing, we can try to guess the proof or guess the certificate. Once we have guessed this certificate, we can ask the verification algorithm to verify if our guess was correct. If the verification algorithm accepts, then the non-deterministic Turing machine would accept. Otherwise, it would reject. Now, if the verification algorithm is a correct verification algorithm, for every string in the language, there is at least one certificate which will be verified by the verification algorithm. Thus, every string that is in the language will be accepted by non-deterministic Turing machine. On the other hand, any string which is not in the language will not be accepted, since no certificate would be verified by the verification algorithm. What we have to do is to argue that this non-deterministic Turing machine runs in non-deterministic polynomial time. Let's look at the details. What we want to show is that A is accepted by some non-deterministic Turing machine N that runs in non-deterministic polynomial time. The machine N will use V as a subroutine. The verification algorithm is a polynomial time running algorithm, so let's say that the verification algorithm runs in time n to the k. Then here is a description of the non-deterministic Turing machine N. On input W of length n, it will guess a certificate C of size at most n to the k. Then it will run the verification algorithm V on the pair W, C. If V accepts, it will accept, otherwise it will reject. So this is a non-deterministic Turing machine, and it clearly accepts the same language as A, because we note that if a string W is in A, then there is some certificate such that V accepts W, C, because V is a verification algorithm for A. Furthermore, since V runs in time n to the k, hence such a certificate cannot have length more than n to the k. Thus, there is at least one branch of our non-deterministic Turing machine, namely the one that picks this correct certificate which accepts W. And therefore, W is accepted by this non-deterministic Turing machine. So what we have shown is if W is in A, then W is accepted by this non-deterministic Turing machine. Now let's see what happens if W is not in A. If W is not in A, then for all C, the verification algorithm will reject W, C. That's what it means to be a correct verification algorithm. If W is not in A, then all certificates are rejected. Thus, all branches of N will reject W. Hence, we have shown that the language of this non-deterministic Turing machine is exactly A. It is also easy to see that this non-deterministic algorithm runs in non-deterministic polynomial time. This whole proof that we have done, the whole proof that if A has a polynomial time verification algorithm, then A is accepted by some non-deterministic Turing machine in polynomial time, and therefore it is in NP, can be summarized in one line. What we can simply say and remember is that we can guess the certificate by using the power of non-determinism and verify it. And this gives us a non-deterministic Turing machine which runs in non-deterministic polynomial time. Now let's prove the other part of this theorem. What we have to show now is that if a language is in NP, then we can find a verification algorithm for it which runs in polynomial time. Now we will show the other side. If A is in NP, then it has a polynomial time verification algorithm. Well, since A is in NP, it is accepted by some non-deterministic Turing machine N that runs in non-deterministic polynomial time. We want to come up with a verification algorithm for A. We do not know anything about the language A. Since we don't know anything about this language A, all we know is that it is accepted by some non-deterministic Turing machine which runs in non-deterministic polynomial time. How can we come up with a verification algorithm for it? Remember that a verification algorithm requires a proof. So how would I prove to you that W is an element of A? Well, the only way I can convince someone is to convince them that this non-deterministic Turing machine accepts this string. So my proof has to somehow convince them that this non-deterministic Turing machine is going to accept the string W. But I can't tell them to run the non-deterministic Turing machine on this string W because they will have to either use non-determinism or simulate the non-deterministic Turing machine using some other method which may take very long. But what I can do is if I can tell them the branch of the non-deterministic Turing machine that leads to an accepting computation, then they can simply check that that particular branch does lead to an accepting final state, and therefore they will be convinced that W is in A. So let us look at the details of this proof. What would be a good proof that W is in A? The only way we can convince someone that W is in A is to convince them that N accepts W. But N is a non-deterministic Turing machine. The main idea is if we give the branch that accepts W, that is an easily verifiable proof that W is accepted by N, and therefore it is a proof that W is in A. Formally, the verification algorithm is the following. On the input W, C, where C specifies a branch of the non-deterministic Turing machine, the verification algorithm simulates N on W by taking the branch given by C. If this particular branch of N accepts, then the verification algorithm accepts, otherwise it rejects. Note that the verification algorithm is a deterministic algorithm. It is not a non-deterministic algorithm. That is because we are actually specifying a whole branch, and this verification algorithm will only follow one branch of the non-deterministic algorithm. Therefore, it is a deterministic algorithm that verifies if W is in A. Let's see, why does it verify that W is in A? Why is it a correct verification algorithm? If W is in A, then the non-deterministic Turing machine accepts W. Therefore, at least one branch of this non-deterministic Turing machine accepts W. That's the very definition of string being accepted by a non-deterministic Turing machine. Hence, we can give the specification of this particular branch to V as C. Then V will simulate N along this branch, and this branch will accept, and therefore V will accept. So the verification algorithm will accept W if it's given the correct branch. On the other hand, if W is not in A, then N does not accept W, and therefore all branches of N reject W. Hence, no matter what branch you give to the verification algorithm, when it simulates W, it will always lead to rejecting that particular proof. Thus, V is a correct verification algorithm, and once again, it's easy to see that V runs in polynomial time, and that's because N runs in non-deterministic polynomial time, and V just follows one particular branch of it. So now we have two characterizations of the class NP. NP is the non-deterministic analog of P. It is the set of all languages accepted by non-deterministic Turing machines that run in non-deterministic polynomial time. Notice that whenever I say that a non-deterministic Turing machine runs, I always say it runs in non-deterministic polynomial time. I never say that a non-deterministic Turing machine runs in polynomial time. That's because I want to emphasize the fact that non-deterministic time does not have any practical analog. We cannot build non-deterministic Turing machines. Therefore, I want to emphasize that it's only a mathematical construct that allows us to understand something. The other characterization now we have of the class NP is in terms of verification algorithms. NP is the set of all languages which have polynomial time verification algorithms. So we have two very interesting classes. One is the class P and the other is the class NP. P is the set of all problems which have polynomial time algorithms. So P is the set of all problems that we can solve in some sense practically. NP is the set of all problems whose solutions we can verify practically. And one of the biggest and the most important question in computer science is if these two classes are equal or not. The most major question in complexity theory is whether P is equal to NP or not. This question is asking if all easily verifiable problems can be solved in polynomial time. This problem is considered to be one of the most major open questions in computer science and also in mathematical logic. The basic idea is if we can verify proofs or if we can verify a language quickly in polynomial time, is it true that we can actually solve that problem in polynomial time? Is it true that we can find a proof in polynomial time? This question is so important that the Clay Mathematical Institute has put a $1 million prize on anyone who will solve this question. Anyone who can prove that P is equal to NP or prove that it is not the case that P is equal to NP, which means they show that P is not equal to NP, they will be given a prize of $1 million. Actually, what I think is the prize money is not important. You can understand the importance of this question from the following fact that the Clay Mathematical Institute has only put prizes on 7 such problems. So, in some sense, the P versus NP question, in some sense, is one of the 7 most important problems in all of mathematical sciences today. It is an extremely important problem, but we seem to be extremely far from finding out the answer. Most computer scientists do believe that the answer to this question is that P is not equal to NP. In fact, Jack Edmonds had written that the Hamiltonian path problem or the Hamiltonian cycle problem does not have a polynomial time algorithm. In fact, he had conjectured this. So Jack Edmonds had conjectured that NP was not equal to P. We will see that his statement is exactly saying that P is not equal to NP. There are many other eminent scientists who believe or conjecture that P is not equal to NP, but we cannot prove this conjecture. This conjecture still remains an open challenge to the whole computer science community. Most of you are graduate students, and this is an extremely important problem. And you should at least think about this problem for a while, try to work on it. I do not guarantee that you would be ever able to solve it, but such important problems one must think about in order to understand what really they are saying and what are the difficulties that one reaches when one tries to solve a question like this. Let us now talk about another notion that we will use, which is the notion of polynomial time reducibility. Remember that we studied reducibility when we were studying computability theory. We said that a problem is reducible to another problem if somehow solving the second problem provided us with a solution to the first problem. That was the notion of reducibility in computability theory. However, now we're doing complexity theory. One of our main issues that we're trying to deal with is resources, time and space. So now we will come up with a new notion of reducibility, which we will call polynomial time reducibility. In computability, it was enough for us that we were able to reduce a problem A into another problem B. In complexity theory, we would insist that not only we are able to reduce the problem A into the problem B, but we should be able to do it quickly enough. That reducing the problem should not take too much time, too many resources. So we come up with this new notion of polynomial time reducibility. A language A is said to be polynomial time reducible to B if we can find a function f that maps sigma star to sigma star such that x is in A if and only if f of x is in B. That is one requirement. The second requirement that we will require of this function f is that f can be computed by a Turing machine that runs in polynomial time. So this notion of reducibility is also measuring time. Now we are saying that we should be able to compute the reducibility quickly. If A is polynomial time reducible to B, then we write A is less than or equal to with a subscript P, B. So this subscript in less than or equal to is reminding us that this reducibility is a polynomial time reducibility. So you have one problem A and another problem B. What you want to do is you want to reduce the problem A into the problem B, but so you want to come up with a function f which will map all the elements of A into the elements of B and all the elements which are not into A into elements which are not in B. But you want to be able to compute this reducibility in polynomial time. You do not want to spend too much time computing this reducibility. If you can find such a function, then you will say that the problem A is reducible to the problem B. Why is that this notion of reducibility is important? Let's look at the following theorem. This theorem says that suppose B is in P. So B is a language which is in the class P for which we have a polynomial time algorithm. And now suppose A is reducible to B in polynomial time, then A is also in P. Let us try to carefully prove this theorem. Well, B is in P, so we have a polynomial time algorithm for the language B, and A is reducible to B. Well, the simple idea is, how can we come up with a polynomial time algorithm for recognizing A? The idea is very simple. We take an instance of A, we apply f to it, and once we have applied f to it, we can find out whether f of x is in B using an algorithm for B, and that should give us a correct algorithm for finding out whether x is in A or not. Let's look at this algorithm and see that it indeed proves that A is in P. So the formal algorithm is, on input x, we compute y is equal to f of x. First of all, we notice that since A is reducible to B, hence there is a function f which maps sigma star to sigma star such that x is in A if and only if f of x is in B. The second thing is f is computed by some Turing machine capital F that runs in polynomial time. Let the running time of this Turing machine capital F be order n to the k. Furthermore, we are given that B is in P. Hence there is a Turing machine M that accepts B in time n to the L. Once again, n to the L is the running time of this Turing machine M that accepts B. Now let us make the following Turing machine that accepts A in polynomial time. On input x, this Turing machine computes y equals f of x using capital F. Then it runs m on y, and if m accepts, it accepts, otherwise it rejects. Clearly, this Turing machine recognizes the language A. Actually, it decides the language A, but how much time does it take? Let's calculate that carefully. Let x be an input of length n. Then computing y, which is equal to f of x using the machine capital F, takes time order n to the k. The second thing we notice is that the length of y cannot be very long. It must be less than or equal to order n to the k. That is because if a Turing machine runs for time order n to the k, it cannot produce an output which is longer than the amount of time it spent computing. Therefore, the length of y is bounded by order n to the k. After that, we run m on y, and that would take time the length of y to the L. Notice we have to be careful. When we run m on y, it does not take time n to the L. It takes time which is proportional to the length of y to the power L. Therefore, running m on y takes time length of y to the L. So how much is the total time? Let's estimate it in terms of n. The total time is order n to the k plus order length of y to the L, which is less than or equal to order n to the k and order n to the k whole to the power L. That's because we have an estimate on the length of y. And this all can be estimated by order n to the kl. Since k and l are constants, therefore k times l is also a constant. Hence, this is a polynomial time algorithm for this language A. Thus, we have been able to show that A is also in the class P. Let's remember this theorem again. We're saying that if B is a language which is in the class P, and if you reduce A in polynomial time to B, then A is also in the class P. Now let us come up with a new notion which is going to be called NP completeness. This notion of NP completeness is extremely important in complexity theory. What we want to do is we want to characterize problems of which we suspect are extremely hard in the class NP. We will call these problems NP complete problems, and we will actually see why these are the hardest problems in the class NP. A language A will be called NP hard if every language in NP is reducible to A. Well, we will call a language NP hard if no matter what language you take in the class NP, that language reduces to this language A in polynomial time. So, an NP hard language would be something very, very special. All the languages in the class NP reduce in polynomial time to this one language that we're calling A. From our previous theorem, if somehow we are able to show that A is in P, or we can come up with a polynomial time algorithm for the language A, we would actually have come up with a polynomial time algorithm for all the languages in NP. Therefore, a NP hard language is going to be a fairly difficult problem to solve. So, NP hard languages in some sense are harder than all the languages in NP. Now let us look at the following definition. We will call a language A NP complete if, first of all, it is NP hard, and the second thing is it itself is an NP. So a language is NP complete if it belongs to the class NP and all the languages in NP reduce to this language A. So if there is an NP complete language, it must be very special. Well, first of all, it is in the class NP. Second of all the languages in the class NP reduce to it. So in some sense, it carries all the complexity of the class NP within it. Everything in NP reduces to it in polynomial time. Of course, an NP complete language would be a wonderful thing because that would be in some sense the hardest problem in NP. All the other problems will reduce to it in polynomial time. Once we had made this definition, it is not even clear that NP complete languages exist. It may be just a definition and there may be no NP complete languages. However, that is not the case. NP complete languages exist, and that is an extremely celebrated theorem of Cook and Levin, one of the most celebrated theorems in computer science, which says that NP complete languages exist. In fact, the theorem points out to us one concrete language and tells us that language is NP complete. Note that if we find an NP complete language, it would be an extremely important language because of the following theorem. If A is NP complete and A is in NP, then P will equal to NP. If somehow I find an NP complete language, I should try to come up with a polynomial time algorithm for that language. And if I succeed, I would have come up with a polynomial time algorithm for all the languages in NP. So an NP-complete language would be such an important problem. So in order for us to solve the P versus NP problem, we will have two approaches provided we can find an NP-complete problem. Suppose we find an NP-complete problem A. Then we know that A is the hardest problem in NP. So either we can try to prove that A is not in the class P. In fact, NP-complete problems will be best candidates for this. Or what we can do is try to find a polynomial time algorithm for A. If we succeed, we will be able to show that P is equal to NP and we'll be able to resolve this question. However, no one has been able to do this. No one has been able to show that an NP-complete problem does not belong to the class P, or no one has been able to come up with a polynomial time algorithm for any NP-complete problem. So now what we are going to do is we will define a language, a concrete language. It will be a very, very concrete problem called satisfiability. And the Cook-Levin theorem states that satisfiability is NP-complete. So it gives us one candidate, which is an NP-complete problem. And this problem is extremely important because if somehow we were able to come up with a polynomial time algorithm for this one problem, we will have a polynomial time algorithm for all the problems in NP. On the other hand, if somehow we are able to show that this problem is not in P, we would have been able to show that P is not equal to NP. So having satisfiability as an NP-complete problem is going to increase our understanding of the class NP a lot. Somehow, the satisfiability problem captures all the complexity of the class NP. Let us define the satisfiability problem. First, we have to start by looking at what a Boolean formula is. You have already looked at Boolean formulas. We were studying logic. You had looked at all kinds of logic. Boolean formulas are extremely simple. What I have done is first put an example for you of a Boolean formula. This formula has 4 variables, x1, x2, x3, and x4. And the formula is x1 or x3 and the negation of x4 or x2 and the negation of x1. Formally, we will define a Boolean formula as follows. Let us take n variables x1 up to xn. We will say that 0, 1 and xi are Boolean formula, and then we will inductively define Boolean formulas by saying that if phi and psi are Boolean formulae, then so are phi and psi, phi or psi, and the negation of phi. So Boolean formulas are nothing but formulas which are made out of Boolean variables in the constant terms 0 and 1, which we are going to interpret as false for 0 and true for 1. And then we have these Boolean connectives which you are very used to of the AND operator, the OR operator, and the NOT operator. And any formula that you can make out of these things is called a Boolean formula. An assignment of variables is just going to be a mapping of the variables to the set 0, 1. Once I give you an assignment of the variables, then what you can do is you can evaluate a Boolean formula. So for example, if I have given you a formula x1 or x2, and then I tell you that x1 is true and x2 is false, then you can evaluate this formula and you can say that this formula evaluates to true. So if I give you assignment of the variables, then a formula can be evaluated. The way a formula is evaluated is we will substitute for each variable the value 0 or 1 as specified by the assignment. And then we will interpret AND, OR, and NOT as we usually do. So for example, if the Boolean formula given to you is phi, which I had written before, and suppose that the assignment tau assigns x1, x2, and x4 the value 0, which is taken to be the same as false, and the variable x3 to be the value 1, then when we plug in these values in the formula, we get a new formula which is 0 or 1 and negation of 0 or the and of 0 and negation of 0. If we evaluate this by interpreting as we do usually, then this whole thing becomes a 0, and we will denote this value by phi and writing down a bar and putting a tau there. So if I give you a Boolean formula and an assignment, you can find out whether this assignment makes the formula evaluate to 0 or to a 1. Notice that if I give you a Boolean formula on n variables, there are 2 to the n possible assignments of the variables. Now we have all the ingredients to define our next problem. The next problem is called satisfiability. A formula phi is called satisfiable if there is at least one assignment, phi tau, such that when we plug in the variables according to the assignment tau, then the formula will evaluate to a 1. So at least one assignment makes the formula true. That's when we call the formula satisfiable, or at least one assignment satisfies the formula. Note that if we have a formula on n variables, then there are potential 2 to the n possible assignments. A formula is satisfiable if at least one of these assignments makes it evaluate to 1 or makes it evaluate to true. So a formula is satisfiable if at least one assignment makes it evaluate to true or 1. There is a very naive, a very simple algorithm which will tell you that a formula is satisfiable or not. This algorithm will take exponential time. Nevertheless, I will describe it to you. What you can do is, if I give you a formula and I ask you if this formula is satisfiable, you go through all 2 to the n possible assignments, assign each variable the values according to each one of those assignments, and evaluate the formula and see if it comes out to be 1 or not. If any one of those assignments makes the formula evaluate to 1, then you will say that that formula is satisfiable. Otherwise, if all of those assignments make the formula evaluate to 0, you'll say that that formula is not satisfiable. Now what we will do is we'll make a problem or a language out of our definition. Let us define SAT, or satisfiability, to be the encodings of all those formulas phi which are satisfiable. It is extremely easy to see that SAT is an NP. Well, we can give an easy verification algorithm. Tell me, what would be a proof that a given formula phi is satisfiable? What would be an easily verifiable proof? Well, a formula is satisfiable if there is an assignment that satisfies the formula. So the assignment would be a very easily verifiable proof that the formula is satisfiable. Thus, we have a very simple verification algorithm. The verification algorithm accepts phi or as an input along with the assignment tau. Then what it does, it plugs in for variables the values as they're dictated by the assignment tau and evaluates it. If this all evaluates to 1, it accepts the input, otherwise it rejects. This is a very simple verification algorithm for SAT. Let's look at it. Input phi comma tau, substitute the variables using the assignment tau. Evaluate the resulting formula, which only now contains constants, zeros and ones. If the formula now evaluates to 1, accept, otherwise reject. This is a verification algorithm for SAT, and it is readily seen that this algorithm runs in polynomial time. The next and the most important theorem that we would study is what we call the Cook-Levin theorem. The Cook-Levin theorem says that SAT, this problem of satisfiability, is NP-complete. Why is this theorem extremely important, and what is the significance of this theorem? Let's think about what we have done. Let's think a little more about what this class NP is. Remember, NP is the set of all problems which have easy verification algorithms. SAT is another problem which is in the class NP. It is a problem which also has a easy verification algorithm. The Cook-Levin theorem says that all problems in NP will reduce to SAT in polynomial time. What it says is, if you have a problem for which you have an easy verification algorithm, you can reduce that problem to satisfiability in polynomial time. In other words, what Cook-Levin theorem is saying is, suppose you were able to find a polynomial time algorithm for this one given problem, satisfiability, then you would have found a polynomial time algorithm for every problem in NP. What the Cook-Levin theorem is saying, let us see what it's saying, is the Hamiltonian path problem is polynomial time reducible to SAT. Why is it saying that? Because we've seen that Hamiltonian path problem is in NP, and Cook-Levin theorem is saying every language in NP is reducible to SAT. So Hamiltonian path is reducible to SAT, clique is reducible to SAT, subset sum problem is reducible to SAT, and composites is reducible to SAT. And not only that, any problem that you can think of in the class NP is reducible to SAT. Furthermore, it has a very interesting consequence. If SAT had a polynomial time algorithm, then there would be a polynomial time algorithm for Hamiltonian path problem. There would also be a polynomial time algorithm for the clique problem. There would be a polynomial time algorithm for the subset sum problem. And there will be a polynomial time algorithm for composites problem. In fact, even more is true. There will be a polynomial time algorithm for all problems in NP. Thus, satisfiability is the most important question, the most important problem in the whole class NP. The Cook-Levin theorem is extremely important because of the following consequence of it. One of the consequences of the Cook-Levin theorem is that P is equal to NP if and only if satisfiability is in P. So the Cook-Levin theorem changes the whole question of studying the class NP into studying this one problem, the problem of satisfiability. This problem is so important that if this problem is in P, then P is equal to NP. And if this problem is not in P, then P is not equal to NP. So somehow the question, the P versus NP question, which was about two classes of problems, two classes of languages, is indeed actually a question about this one problem called satisfiability. If this problem, satisfiability, has a polynomial time algorithm, then all problems in NP have a polynomial time algorithm. If this problem doesn't, then P is not equal to NP. Next time we would look at the proof of the Cook-Levin theorem. The Cook-Levin theorem has a reasonably elaborate proof. However, it is once understood, it's an extremely transparent proof and a very beautiful proof. After that, we will start developing the theory of NP completeness. What Cook and Levin did was hunted out, found one NP complete problem, and they proved that this problem was indeed NP complete. Well, after this, people started searching for more NP complete problems, and they were able to find lots and lots of NP complete problems. In fact, Hamiltonian path, clique, and subset sum are three other problems which are known to be NP complete, and in fact we will prove that these problems are NP complete. However, the technique is going to be very different from the Cook-Levin theorem. Cook and Levin had to prove that everything in NP reduces to satisfiability. When we prove, for example, that Hamiltonian path is NP complete, we will simply reduce satisfiability to Hamiltonian path. This would show that everything is in NP is reducible to the Hamiltonian path problem because it is reducible to SAT, which is reducible to the Hamiltonian path problem. The theory of NP completeness is extremely beautiful. It identifies a large class of problems that are all polynomial time reducible to each other. Furthermore, if you solve any one of them in polynomial time, you solve all of them in polynomial time. Thus, when you work on an NP-complete problem, when you're trying to find a polynomial time algorithm for an NP-complete problem, you should remember that you're not working on that one problem alone, but an entire class of problems. These problems are so general. Well, in the next lecture, we will look at the proof of Cook-Levin theorem and discuss more on NP completeness. I'll see you next time. Thank you and goodbye.